First thing is exam 3 is a week from today. Once we get farther into this week, I'll decide whether we're going to have rotating coordinate systems on this or not. Okay, so let's just get into some problems, and I'm going to just try to keep being consistent in how we approach it. And I think you'll find once you've done a few of these problems, if you're thinking about them right, it's gonna start to feel sort of mechanical, but it's such a, and then that's how you want it to feel like every problem is the same. But okay, so let's say, we have a bar that's rotating this way, and it's connected to a thing that rotates around it like this. Okay, so let's say this one has an angular velocity of 5 radians per second. And let's say it's slowing down really fast. So let's say 40 radians per second squared. And this other body is rotating about an axis like this, so it's going sort of circling into and out of the page. Okay. And let's say that this is rotating fast at, let's say, 20 radians per second. We'll give this stuff some dimensions. Let's say this one's 1 meter. Let's say this one's 0.8 meters. And let's say we want to calculate the acceleration of this point, p. Okay, so the first question you should ask yourself when you see multiple bodies like this, and we're going to be thinking about this with bodies where one body is riding the other body, okay? The first thing you want to ask yourself is identify which one is kind of the base body, which one is the body that's riding the other one, okay? And once you do that, the question is, does the orientation of that base body, I call it the horse, like the horse and the cowboy rides the horse, does the orientation of the horse determine the axis of rotation of the cowboy or not? Okay, so let me give you a couple examples. Like if, I'm gonna erase this in a second to get this out of your notes, but okay, so think about a setup like this. Okay, and this is rotating like this, and this is rotating like that. Okay, so at the orientation here, what's the axis of rotation of the cowboy? Yeah, it's out of the board, right? Okay, now think about changing the orientation of the horse. and think about the axis of rotation of the cowboy. Say the horse is over here now. What's the axis of rotation of the cowboy?
Still Z.
Still Z. So this is not one where you have to use a rotating coordinate system. You've done problems like this for a long time now. Okay? Question about that?
No, I'm just thinking about the weekly assignment.
Yeah. Okay.
Problem 3 on there.
Okay. Well, yeah, so on the weekly assignment, oh, God. You guys. Yes, okay. This is, I'm sorry. Don't do number 3 on the weekly assignment. That was a mistake. I put it up there, and after I put it up, I noticed that there was a third problem that I didn't see before. I went and deleted it, reposted it, but apparently people had already downloaded the thing. So the weekly assignment, you're only doing problems 1 and 2. Okay? But yeah, problem 3 in the weekly assignment that you should not do, that'll come up on the next weekly assignment, is a case where you have to use rotating coordinate system. Okay, so does everyone agree? Can everybody see how the orientation of the horse, in this case, has no effect on the axis of rotation of the cowboy? Okay? So this is old stuff. This is easy stuff. You did this when you were much younger. Okay? But now compare that to this example that we're doing. Okay, at the instant shown, what's the axis of rotation of the cowboy? I drew it, it's straight down, right? Now imagine this oriented over here. The horse is oriented over here. Does that change the axis of rotation of the cowboy? Yes. So in problems like this, you have to use a rotating coordinate system, okay? And the rotating coordinate system has to be fixed to the horse, okay? Anybody have any questions to help clarify that? Yeah.
So our rotating coordinate system, where should we normally put that? Should we put that at the center of rotation of the horse?
Yeah, good question. And that's a really important question. So the first question is, does the orientation of the horse affect the axis of rotation of the cowboy? In this case, it does. So we're going to have to use a rotating coordinate system approach. And the CS has to be fixed to the horse. Okay? But then that brings up the next question. So there are infinitely many points on the horse. Where do we want to put the origin of the coordinate system? And the answer is, by being careful, you could put it anywhere. But there's one clear preferred spot to put it. You want to put it at the point on the horse where that origin would have 0 acceleration. Okay? So we want to put the origin here. Okay? We could do this problem with the origin here, say. Okay, as long as it's fixed to the horse, we could still do this problem. But then what's going on is that origin is accelerating. Okay? Besides rotating, that origin is moving in circular motion, which means that origin is accelerating. And so we have to use relative motion to deal with that on top of the fact that that we're using a rotating coordinate system thing. We prefer not to do that, you know. So I'll do some examples like that later once we get used to the basic idea. I think it can sort of help your understanding. But never in your life will you, if you're just trying to solve a problem, you would never want to do anything but put the origin at that fixed point. Okay? So with the origin at the fixed point. Okay, so we're going to use a coordinate system that's fixed up there, you know, like, so if this is the body, we'll use a coordinate system like this. Okay. And now that means that capital omega and capital omega dot are motions of the horse. Okay. And lowercase omega and alpha are motions of the cowboy. Okay? And every problem is like this. So now we know we're going to use the equation that says the acceleration of p is equal to the observed acceleration of p. This is like if that green coordinate system was a video camera, this is the acceleration that video camera would see. Okay? Plus capital omega dot crossed with the position vector of p. Plus 2 times capital omega crossed velocity of p that's observed. Plus capital omega cross quantity capital omega cross p. And now the way to think about this is just collect all these pieces, okay? So we're just gonna write down all the pieces, and like in office hours on Friday, a couple people were noticing like, hey, I could just put a program in my calculator that does all this. The only thinking that a human has to do is collecting the pieces. You know, your calculator can cross and multiply and, you know, add and all that stuff. So let's just start putting these pieces together. Okay, so first, our capital omega, that's the angular velocity of what, the horse or the cowboy?
Horse.
Horse, right. So that is, it's not super clear which one of these corresponds to what. This is supposed to be this one. This is supposed to be this one. Okay, so 5 radians per second in the positive z direction. Now capital omega dot. That is the angular acceleration of the coordinate system. So that is the 40 radians per second squared in the negative z. Okay? With me on that? And in this first set of things, let's also collect the position vector of that point P. Okay, so the coordinate system is up at the hinge. in that coordinate system, what's the position of P? -1 in the y direction, -0.8 in the x direction. Now we have to think about the observed motions. Okay. So what is that coordinate system C for a velocity of the point P? So notice, I think a nice way to always think about those observed motions is to think, okay, temporarily, we're gonna pretend this isn't moving at all. And we're gonna analyze the motion of P as if this is just fixed, okay? So then this P is just in a circular motion around the y-axis, right? Are you with me on that? I guess it's the negative y-axis because of the right-hand rule. So V observed I guess I wrote it as V of P that's observed is going to be equal to a lowercase omega cross R. Okay, so now we have to think of what those two things are. Lowercase omega is the angular velocity of the cowboy. So that's 20 in the negative y direction. And R, I can't stress this enough, R and P are not the same thing. They can be sometimes, but in general, they're not the same thing. So remember that R is the vector that goes from the center of the circular motion to the point you care about. Okay, so what's R? If we're assuming that there's no, that the vertical piece is fixed for now.
Just -1.8.
Yeah, in the x direction, exactly. And so the velocity of P observed is equal to 0, -20, 0, crossed with -0.800. And so that is 0, 0, -16. Okay, and now we'll go to the observed acceleration. These observed things in problems like this are always circular motion, so this is going to be the watermelon equation. So we got alpha cross R plus omega cross quantity omega cross R. Alpha is the angular acceleration of the cowboy. What's that in this problem? Yes. 0. Yep, I didn't give one of those. So this part goes away. We already have omega and R. And so the acceleration of P that's observed in the coordinate system is equal to 0, -20, 0, crossed with omega cross R. Well, that's what we got for the velocity, so this is, well, I'll write it like this first. So this is 0, negative 20, 0, crossed with 0, 0, negative 16. And so that is 320, 0, 0. Now we have all the pieces and we're just plugging it into that big equation. So the acceleration of p is equal to 320, 0, 0 plus capital Omega dot crossed with the position vector. So 0, 0, negative 40 crossed with negative 0.8, negative 1, 0. Plus 2 times omega, capital Omega, 0.005, crossed with the observed velocity, plus capital Omega cross quantity, capital Omega cross P. So 0.005 crossed with the quantity 0.005 cross negative 0.8, negative 1, 0. And whatever that comes out to be, that's your answer. Well, let's do this. Matt or Dan, either of you guys happen to have this in your calculator, this formula? Okay, so what? D2L, no, it's not.
If we make a file, do you want us to send it to you so that we can download it?
Yeah, that'd be awesome. Yeah, thank you. Yeah, everybody with the different calculators, send it to me in your calculator. So what do we got? 500 for this. Nope. Yes, 505. Not 00. We do have 5. Then we have negative 4. And then 0. So these two together, we have positive 20, positive 25, 0. I think that's right. For this one, we have these two vectors are parallel, so this is 0. For this one, we have minus 40, positive 32, 0. And so add those all together and you get an acceleration of p that's equal to 25, negative 15. So I think this is 305. Then 53, 0. Yeah.
Just a quick order of operations question.
Yeah.
So the two vectors that were parallel,
Yeah.
if they weren't, do you multiply the 2 into the matrix?
Yeah.
Matrix, first and then cross product?
The scalars you can do you can multiply to anything. That totally can move around. The only thing that matters is the order of the cross product.
Cool.
Yeah. Any questions about that?
Can we look at how we found the observed again?
Yeah.
Didn't really understand how the place are.
Oh, okay. Well, so when you're talking about any of the observed stuff, you just don't care about anything the horse is doing. Because the observed means it's just what the camera sees. So like as this thing's moving around, the camera's moving around with it. Okay? And so all that camera sees, no matter what the horse is doing, is this P moving around the y-axis.
Is the rod rotating as well?
It's not rotating, but it's doing this. This thing is spinning around.
Oh, I see, okay.
Yeah. So that camera, think of what that camera sees. If this camera is pointing straight down and it's fixed to this body, no matter where this goes, the camera is looking straight down that vertical member. You know what I mean?
Yep.
And so no matter where this vertical rod goes, all that camera sees is this thing in circular motion. So that's why you can just forget about this and just think about this for the observed stuff.
Okay.
Yeah.
Can you add the omega cross P program? I had
You got something else?
307 and 305.
Okay, did I add? You got 3.0 what?
I got 357 and 0.
Oh, 357.
Sorry, 300, comma, 57, comma, 0.
Oh, 300. Okay, so we got minus 20. Oh yeah, I think I added the wrong one there. I think you're right. Okay, so we only have 1, 2, 3 terms. We got 320, 280, 300. Yeah, I think that's what I did. And then 32 plus 25, 57. Thank you. You are right. By the way, in this class and in Physics 1, I'm guessing you only talked about centripetal acceleration. You didn't talk about centrifugal force, even though that's the one that people hear about more often. The centrifugal force, or the centrifugal acceleration, is that 57 there, the difference between the observed acceleration and the true acceleration along the motion of that, like in the radial direction from that big circular motion. So I'll talk about that a little more. It's not really useful for calculations in any way. It's just more useful because you hear that word and it can be confusing, Yes?
Does that also cover the difference between the 320 and the 300?
Well, yeah, then that's the centrifugal motion of the other body.
Oh,
Like it's always opposite direction of the centripetal acceleration. I'll do an example where that's more clear. Any other questions about that one? All right, let's just do another example. Okay, so let's say we have a rod like this. Connected to a disc. Hmm. Okay, you with me on that? And the disc is rotating around this way at 20 radians per second. And the arm is rotating around this way at 40 radians per second. And let's say it also has an angular acceleration of 100 radians per second squared in that same direction. And we'll give these some small dimensions. So let's say this is 0.01 meters, and this is 0.02 meters. And we want to calculate the acceleration of this point P. Okay, there's two bodies, and so that disc, it would get pretty cluttered if I tried to draw that, but you can imagine the center of that disc is on a hinge that's spinning around on the floor like a carousel kind of thing, okay? And then in the meantime, this arm is also rotating around its hinge. Can everyone follow what's going on in the problem? And so first thing we have to do is identify the horse and the cowboy. What's the horse? Yep. And the cowboy is the arm. And now ask yourself, does the orientation of the horse affect the axis of rotation of the cowboy? It does. You know, all you have to do is imagine two different orientations 90 degrees apart or something like that, and think like, does the axis of rotation of the thing that's riding change? Here, the axis of rotation is, well, into the board. If you went over here, the axis of rotation would be sideways. So yeah, that means we have to use a rotating coordinate system. So the orientation of the horse determines the axis of rotation of the cowboy. So we do have to use a rotating coordinate system fixed to the disc. And where do we want the origin to be?
Really connect.
Yeah, at that fixed point on the disc at the center. Okay, so I'll use a coordinate system like this, where that's X, Y, and Z. And we know we're going to use the formula acceleration is equal to acceleration observed plus capital omega cross P plus 2 times capital omega crossed with the observed velocity plus capital omega cross quantity, capital omega cross P. And again, now we just have to go through and get all these separate pieces. So first, capital omega. That's always the angular velocity of the horse. That's the disk. So what's the angular velocity of the disk? I have 0, 20, 0, the way I have it oriented. And then the angular acceleration of the disk. There's no angular acceleration.
So there's not a formula defined at omega dot.
Omega and omega dot just have to be given. I mean, I suppose you could make a problem where you had to plug variables into the equation and back calculate some of this stuff, you know, but actually none of my problems have done that in the past, but there's a first time for everything. But you know what I mean? But you can picture what I'm talking about, right? Like, oh,
If you're given everything else.
yeah.
Okay.
I mean, you could actually use you could use an accelerometer at the point P to calculate the true acceleration and then know everything except the angular acceleration of the disk or something and back calculate it. But
And you can just put an accelerometer in the disk.
yeah, but you can't always get to everything yeah, right. But you cannot always get to everything you want, you know? Like a lot of times, I mean, I know this from work experience, a lot of times where you put your cameras and stuff is determined by what'll hold a camera or where you have vision of stuff, you know? So yes, in a thought experiment, that's true, but not always in reality, yeah. Okay. But as far as like, yeah, a smart ass answer to my comment, yes, that's a good one. Okay, and then P. So remember, we're looking for the position vector of that point P. So it's going to be 0.1 in the positive Z direction, and then 0.01 in the positive Z direction, and then 0.02 in the positive Y. So 0, 0.02, 0.01. And now we have to calculate the relative stuff. So the velocity of P, the observed stuff. The velocity of P that's observed is lowercase omega, this refers to the cowboy, cross R. And so now we have to come up with those. Lowercase omega is what? Yes, 0, 0, negative 40. And the r vector, that's the vector from the center of the circular motion to the point. What's that?
0.020.
0, right, 0.020, very good. And so now we can plug these in, and the velocity of P observed is 0, 0, negative 40, crossed with 0.020, and you get positive 0.800, I think. And now we'll do it for the observed acceleration. This is alpha cross r plus omega cross quantity omega cross r. Do we have an alpha? Yeah, in this case, it's 0, 0, negative 100. Our omega is 0, 0, negative 40. R is 0.020. So this is 0, 0, negative 100 crossed with 0.020 plus 0, 0, negative 40 crossed with what we got in the last one, 0.800. And we get 2, 0, 0 plus 0, negative 32, 0. So 2, negative 32, 0. And now we have all the pieces we need. So the total acceleration of P is equal to 2, negative 32, 0 plus our capital omega dot is 0, so this thing goes away. Plus 2 times capital omega crossed with that observed velocity plus 0, 20, 0 cross quantity 0, 20, 0 crossed with the P vector 0, 0.02, 0.01. This one, let me put this above, is 0.200. And so this thing altogether is -4, so 0, 0, -4, I believe. This one is 0, 0, -32, if you multiply that 2 in there. And so the acceleration of that point P is 2, -32, -36. And the thing about going through all this is that now, you know, the whole idea of this is now we have an acceleration that is going to satisfy Newton's laws. So if you had something, you had some sensitive piece of equipment up here at P, and you knew it could only withstand a certain amount of external force, you know, without breaking it, you could plug that now into Newton's second law, calculate the external forces on it, calculate, you know, whatever the thing fixing it in there has to apply to hold it in place during that motion, and see whether that's, you know, allowable or not. So the whole idea of this is coming up with an acceleration that's measured by an inertial coordinate system, even though our camera, the thing really taking measurements, is not an inertial coordinate system. Okay? Anybody have any questions about that?
Will we be dealing with, like 3 bodies, for instance?
Yeah, good question. We will not, but you can sort of piggyback this idea to as many bodies as you want. But we were just talking about this in office hours on Friday, and I'd have to take some time to think about which way you piggyback it. I know I've thought about that before, but I don't remember. But the basic idea is you go through all this, you calculate this acceleration, and now you say, okay, that's not a true acceleration. That's an observed acceleration, and now you can yeah. And I can't remember if you need to go forward starting at the fixed point, or if you need to start at the extreme and work your way backwards. But anyways, yes, you can do it, but we're not going to.
Okay.
Any other questions? Okay, that's all.